Okay, well, good afternoon, everyone. Thanks for joining. As Abdul mentioned, I'm going to be talking about multi-level Markov chain Monte Carlo methods for Bayesian inverse problems. I should mention that this is joint work with Fabio and with Professor Raul Tempone. So let's get started. So what is a Bayesian inverse problem? Well, given some measured data y that we can model as y equals f of u plus e, where u is a set of unknown parameters with some known distribution mu prior. F is a mathematical model of the physical process that generated the data. It can be thought of as a forward model of a forward mapping between the parameter space x and the data space y, and e is some random noise with known distribution mu noise. The goal of a Bayesian inverse problem is to sample this set of unknown parameters u, conditioned on this noise-polluted measured data y, from its posterior distribution that I denote as mu y, that can typically be written in terms of a likelihood times a prior, where here the likelihood measures somewhat the misfit between y and f evaluated at u, and the prior encodes the information that we have on this set of unknown parameters before any data has been observed. Typically, this is typically written, in terms of its the radon-occurring derivative of the posterior with respect to the prior, given here, which typically, depending on the choice of the noise model, just depends on this misfit between y and f evaluated at u at some given y. Now, there's a caveat with this formulation, and it is that typically this mathematical model F needs to get evaluated numerically with a discretization parameter L with high accuracy and cost. And this in turn induces a discretized forward operator or forward mapping FL, which in turn changes the problem a little bit in the sense that now our potential function here, phi L, depends on this discretized forward operator FL, which in turn induces this sort of discretized posterior, if you will, mu YL, with the understanding that as our accuracy or as our model becomes more and more accurate, as L goes to infinity, our sort of discretized posterior converges to a true posterior mu y. Now we want to sample from this posterior. Perhaps the best way of doing so is using Markov chain Monte Carlo method. So we create a Markov chain whose invariant distribution is the distribution that we ultimately want to sample from or are able to sample from, so mu YL in this case. And perhaps the best known Markov chain Monte Carlo method is the Metropolis Hastings algorithm, which, in case you're not familiar with it, like 0.1% chance, it works by taking these two steps iteratively. You first propose a candidate state set from a proposal distribution Q that you know how to sample from. And then you set this candidate state set as the new state of the chain with probability alpha L. And otherwise you reject it and stay at the current state of the chain. What's important to mention here is that to evaluate this acceptance probability alpha L, one needs to evaluate this posterior density at each new candidate state, which in turn will require that we evaluate this forward mathematical model FL here. Okay, in short, just to introduce some notation that might be a bit useful later, this whole procedure induces a Markov transition kernel P, which in broad terms can be understood as this probability distribution that depends on UN, from which we sample the next state of the chain, UN plus 1. And once a sufficiently long chain has been obtained, we can compute expectations with respect to the posterior distribution mu y, or we can approximate this posterior expectation here by approximating it as an expectation with respect to the discretized posterior distribution mu YL. And we can then in turn estimate this expectation here in terms of the usual ergodic estimator, just for the people online, in terms of the usual ergodic estimator obtained from samples that we got from this algorithm. Now, it is probably clear to everyone that the accuracy of this estimator is controlled by two factors, n, which is the number of samples, and L, which is the discretization parameter. And this poses an issue in the sense that typically n is very, very large, and for many applications of interest, this forward model FL is very, very expensive. So the overall cost of this Bayesian inversion is, or this MCMC algorithm is going to be quite large. So there's a lot of work aimed at alleviating these issues. Of course, because of the topic of the workshop, we're going to focus on multi-level MCMC methods. So what is the idea here? Well, instead of considering a fixed forward operator F at a fixed discretization F capital L, we introduce a hierarchy of discretization models F induced by this curly L here with increasing accuracy and cost, in the sense that as L goes to infinity, our FL converges to the true forward operator F. And well, here just to illustrate, when L is 0, our model is very inaccurate, but very cheap to evaluate. And as we go deeper on the levels, it becomes more and more accurate, but also more expensive. So nothing too groundbreaking there. Now, by inducing this family of forward operators, we induce a family of posterior measures mu y L that have this typical form here, where the level goes through the forward operator on this potential. Okay, once we have introduced that, we can go back to our original problem of estimating this posterior expectation here by, again, approximating it with as an expectation with respect to this discretized posterior, which we can then write in terms of this usual telescoping sum in multi-level methods. Now, there's a small but significant difference here, and it is that in this telescoping sum, when one is in the multi-level Markov chain Monte Carlo, these expectations are with respect to the posterior level L, and this is an expectation with respect to the posterior level L-1, which will make things a bit more complicated than in the multi-level Monte Carlo case. Okay, and once we have written it, this expectation here in terms of this telescoping sum, we can estimate each of these terms in terms of their ergodic estimators, where again, the samples from these orange terms here are samples from posterior mu y L, and the samples from these blue terms here are samples from posterior mu y L-1, which are measures that look kind of like each other, but that are not exactly the same. Okay, and why do we want to do this? Well, it's a fact that if one samples less and less as one goes deeper on the levels, one can obtain a multi-level MCMC estimator with the same accuracy as a single level MCMC estimator, however, with a much cheaper cost. And in fact, there is some theory to back this up, proposed on this seminal work by Tim and Rob and co-workers, which basically states that if one has this sort of convergence of the means, if one has this sort of decay on the variances of this difference here YL, if the mean square error of an estimator of this guy decays, well, can be bounded in terms of this variance, and if the cost associated with sampling a quantity of interest at level L increases as we go deeper on the levels, then it was shown by Rob and collaborators that the cost associated with having a multi-level MCMC estimator with a mean square error smaller than tolerance square grows in this form, which is quite similar to the, let's say, canonical complexity theorem on multi-level Monte Carlo with this additional log term here. And conversely, if one does a single level estimator, the complexity looks kind of like this. So I know everyone here is an expert on these methods, but just to illustrate it a bit better, if one is doing multi-level MCMC, one would get a complexity that grows as either one of these three curves. Meanwhile, in the single level case, one will get a complexity that grows in terms of tolerance as the spread curve. Now, there is a difficulty here that's not as apparent, or that just doesn't happen as much on multi-level Monte Carlo, and it is that we need this variance term, the variance of this term here, to go to 0 as we go deeper on the levels. And this is not immediately obvious, or it's not super easy to do, in the sense that, again, this is a sample from a posterior distribution at level, well, from a posterior distribution mu YL, and this is a posterior distribution mu YL -1. So you cannot just sample, you cannot create these chains independently of each other. One needs to sort of create chains that are coupled, whose paths kind of take the same trajectory. And the way that we couple these chains, which is the crux of these multi-level MCMC algorithms, to generate this coupled chain so that this term indeed goes to 0, and so these chains spend more and more time close to each other, The way that we do that is to couple them. We couple them by coupling the proposals in the Metropolis Hastings algorithm. Okay, so just to give a little bit of detail on what coupling means, we say that gamma is a coupling of two probability distributions Q and R if a joint sample U prime L minus 1 U prime L. If this is a sample from gamma, it has the right marginals. So in this setting, UL minus 1 is a sample from R and UL is a sample from Q. And we know that for any coupling, the probability of sampling this joint state and having each component being different from each other is larger than or equal than the TV distance between Q and R. And we say that a coupling for which this here happens with equality is a maximal coupling. So in particular, what we would do is that we're going to use maximal couplings of the proposals to couple well, the chains on the multi-level MCMC algorithm, or in this part of the telescoping side. And broadly speaking, sampling from maximal couplings is not too terrible if one has these that this holds with equality, and one wants to generate a maximal coupling between this probability distribution R and Q. One can think of implementing this algorithm that roughly works as sampling the same state with probability proportional to these this shaded region here, and otherwise sampling something that is not the same. In our work, we looked at two particular types of couplings. The first one we call the independent Metropolis Hastings coupling, for which we create this coupling again by using a proposal distribution that is independent of the current state of either chain. And a second coupling mechanism that we looked at is the maximal coupling between two possible state-dependent proposal distribution Q and R, so it can be a PCN or a random walk Metropolis. That I know that Cody and Jasra and Hang have also worked a bit on it as well. Okay, so let's give a little bit of details about the independent Metropolis Hastings. So the idea here is to couple chains by always proposing the same states independently of the current state of either chain. So this algorithm is relatively simple. It kind of looks like as follows. So you sample a candidate state set from a proposal distribution Q, and you sample a uniform number W between 0 and 1. And then for each of the two levels that you want to couple, you set as the next state of either chain with the usual Metropolis Hastings accept rejects ratio, well, with the usual Metropolis Hastings accept reject probability alpha j, comparing with respect to the same number W. Now, just to introduce some notation, this induces a joint kernel PLIMH. Of course, the choice of QL is critical, as with most MCMC algorithms, and in particular, most or all independent Metropolis Hastings type of algorithms. This procedure here can be thought of as a sort of generalization to Rob's method, in the sense that in such paper, what they were doing is that as a proposal, they take this empirical distribution, well, they subsample basically from the chains obtained at the previous level, which is a distribution that sort of, well, that approximates the procedure at level L-1. However, one can show that in some cases that this can give biased results, and this bias might not be negligible. What we did in this work was to extend this methodology to a wider class of proposals that satisfy certain conditions, and that can be given by, say, a prior, a KDE, a Laplace approximation. However, admittedly, they're not always easy to construct or to verify these assumptions. Now, the second maximal coupling algorithm that we looked at, that admittedly Hang and all got ahead of us and published it first, is a maximal coupling of state-dependent proposals. So here, if my proposal, if I take my Qn and Rn to be these state-dependent proposals, so again, as a random walk Metropolis or a PCN algorithm, the procedure looks quite similar. So essentially, we sample this joint state from this maximal coupling gamma n. We sample this uniform random number W from this uniform distribution 0, 1. And again, we accept or reject each component of this joint state as the next state of each chain with the usual Metropolis accept reject procedure, comparing with respect to the same uniform random number W. Now, this induces, for notation that I might use later, a joint transition kernel ML-MCMC. And again, this is a multi-level MCMC with state-dependent proposals. So methodologically, it's a little bit different from Rob's algorithm or from Tim's algorithm in the sense that you don't always have to subsample or propose independently. Now, there's a drawback of this method, and it is that it proposes the same state with probability given by this, so 1 minus the TV distance. And this term here can become small if both chains are too far apart. And again, why do we want them to propose the same state? Well, because if you propose the same state to both chains and it gets accepted, then the chains get synchronized, and then these terms start becoming smaller and smaller. Okay, so some of the things that we looked at or that we focused the most on was in getting some theoretical results for this. So I'm just going to present a couple of results that we got. So the first one is regarding the convergence of the joint IMH chain. So we have that if there exists a C independent of the levels such that this minorization condition holds, meaning that the proposal has fatter tails than the target posterior. And for all levels, there exists a unique invariant measure well induced by this Markov transition kernel. And furthermore, we have uniform ergodicity, or that the chain converges uniformly ergodic to such a measure with a rate given by this C. Conversely, if this condition here, if this minorization condition here doesn't hold, then one can show that the algorithm is indeed not geometrically ergodic, which it doesn't mean that it's not going to work at all, that is going to give you completely terrible results, but it does mean that it will give you some bias that might not go away in a reasonable amount of time, which might be a very small bias.
Notation in the soup, there is something below the soup. What does it mean?
So F in the L infinity norm
is less than 1.
Yeah, it should be less than 1, sorry. The supremum over F less than 1 in the L infinity norm.
I cannot hear you acoustically.
The supremum over F, the norm of F being smaller than 1 in the L infinity norm.
Less than 1. F is an element of x2, yeah? What is x2? What is x2?
Is the Cartesian product of the parameter space with itself.
F has only one argument in the integrand, so what does it mean?
Yeah, I should mention that. So it's probably difficult to see, but this is a boldface U prime, meaning that it has this component UL minus 1. No, sorry, I should have made that more clear.
Differential is only with respect to UL prime, yeah.
It's for all UL. It's for all UL.
Mm-hmm. And okay, so just to reiterate here, so if this condition holds, we have uniform ergodicity with a given rate. Otherwise, we don't have geometric ergodicity or uniform ergodicity for that matter, which might give you a small bias that might just not go away in a reasonable amount of time. And why is this result important? Well, first of all, it's the first result of its kind, meaning that I think is the first time that someone looked at whether these algorithm for the multi-level MCMC induced a joint measure, and whether this measure existed, was unique, and it converged to it. It provides a guideline of the implementation because, well, you should aim to satisfy this A1, or should at least see whether one can try to satisfy this. And third curiosity, I would say, is that this invariant measure nu L is induced by the proposal, meaning that the invariant measure sort of depends on the proposal, which is definitely not the case in the single level counterpart. We have a similar result for the maximal coupled MCMC algorithm, multi-level MCMC algorithm. So if we assume that the potential is strictly positive, that we have Gaussian priors, and that we have sort of PCM proposals on each marginal, together with some technical assumptions on the convergence of these marginal PCNs, then we can get a similar result in the sense that we can show that there exists a unique invariant measure nu L induced by this algorithm. And furthermore, we can show that we have geometric ergodicity, or that the chain converges geometrically ergodic to this measure nu L. It's a slightly weaker type of convergence. Now, another result that we got that is not only applicable to the multi-level MCMC context was that if one has a mu invariant Markov transition kernel P that is not necessarily reversible and the chain is mixing sufficiently fast in a very informal way, then one can indeed bound the mean square error or the non-asymptotic mean square error of an estimate of this estimator F in terms of its variance here, where this constant depends on how fast this chain is mixing. And why is this important? Well, it's useful beyond multi-level MCMC. It's needed for the complexity result of Rob and al, where one of the conditions that need to be satisfied is this one right here. And it's worth mentioning that similar results exist in the literature, particularly on the thesis by Daniel Rudolph. However, they rely upon assumptions that are difficult to verify when the chains are not reversible. And if you think about it, these chains in this multi-level MCMC are not reversible in the sense that as you go deeper on the levels, you start to concentrate more and more in the diagonal, or you should be concentrating more and more in the diagonal. So this reversibility condition that the probability of moving from a set A to a set B should be the same as from a set B to a set A starts becoming, well, it starts to make less and less sense as you go deeper on. One result regarding the complexity is that if one has this sort of convergence on the potentials, on the quantities of interest, and some integrability conditions on the quantity of interest and on the proposals, then one can show that these three conditions on Rob's theorem are satisfied for a general Q with a particular form for AUW here and for beta. And again, this is important because one can show that Rob's complexity result can be extended to other proposals that are not just something part of the previous stuff. We were also able to show some similar results for the maximal coupling algorithm. However, they rely upon much stronger assumptions, so I'm not going to mention them. Okay, I'm probably going to skip this part. Okay, so just in the interest of time, I'll just skip to numerical examples. So here, given this Darcy subsurface flow, in case you missed it the last 1,000 times, the goal is to find the posterior distribution of the permeability field kappa, well, given by EUW in a domain D, given noisy measurements of the pressure head H, so the solution of this equation. And given this permeability, this posterior distribution, we aim at estimating this posterior expectation here of this quantity of interest, which can be understood as the log flux across one of the boundaries of the domain. Okay, so to generate data, we introduce a finite element mesh with some given elements, and we generate data Y by solving this PD here with some given value of U true, randomly generated value of U true from mu prior, given by this, and observing the solution at 100 different points in the domain and polluting those observations with 1% Gaussian noise. And to test our methodologies, we introduced 4 discretization levels ranging from L = 0 to 3. each of them in their own finite element mesh given by this, which in turn induced a posterior of this form where again the prior here is a Gaussian distribution. And in particular, we compared our IMH algorithm using a Laplace approximation and our maximal coupling algorithm using this generalized precondition Crank-Nicolson, so kind of like a shifted Crank-Nicolson that takes information from the Laplace approximation. Just to maybe illustrate what this map here, this maximal posterior point here looks like. If this is U true, the map at level 2 kind of looks like this. So you kind of see that it kind of gets the most relevant features of. Okay, so just to verify our algorithms, we, again, just to reiterate, one of the things that we're most interested on is to see that they actually concentrate around this line y equals x. And as we can see, that is the case for both methods. So here in this row here, it's the one for independent Metropolis Hastings, and in this row is the one for we have the one for the maximal coupling algorithm. And in both cases, as we go deeper on the levels, these samples become more and more concentrated in or around the diagonal. So here for the maximal coupling, it becomes concentrated around the diagonal, so not exactly there, but kind of there. And similarly for the independent Metropolis Hastings, where the concentration in the independent Metropolis Hastings case is, of course, a bit better than in the maximal coupling. Given this, we can also estimate the rates on this complexity result, so beta and gamma, beta, alpha and beta, and so we have them here for both IMH and MXC. And as we can see, for both methods, we get more or less the same, or actually the same rate for this decay on the means. However, we get that the independent Metropolis Hastings case has a slightly better or a slightly faster decay on this difference on the variances. And the reason why is, again, this independent Metropolis Hastings method, if the proposal is quite good, is going to rejoin the chains more often than, say, the maximal coupled one, which will make more. Okay, and once this rate have been estimated, one can, of course, compute like what is the complexity of these methods, like how many samples one would need to obtain an estimator up to a given tolerance. So if we compare those with respect to their single level counterpart, we get something that looks like this. So here in the green one and the blue one, we have both versions of the multi-level MCMC algorithm that we implemented. And here on the orange one and the white one, we have their single level counterpart. Okay, just to conclude or to summarize, we proposed two methods that can be understood as generalizations of current multi-level MCMC techniques, or current by the time that I wrote this. The first one can be understood as an extension of the subsampling approach, which allows for a wider class of proposals. The second one can be understood as a class of multi-level MCMC that allows for state-dependent proposals. We presented a theoretical analysis for the convergence and cost for both proposed methods, although admittedly the one for MXC can be refined. I didn't touch up on 3 for time reasons, but I would mention that the maximal coupling algorithm, this coupling procedure between the proposals, is easy to implement, but it can lead to a lower performance than a subsampling or a good IMH whenever they're both applicable. Now, in terms of perspectives, some things that are not immediately obvious to me or that it would be nice to discuss are whether these results extend to more recent methods, such as the one that Tim proposed yesterday. I don't know if this is a trivial, if it would be a trivial extension to it. Another interesting idea would be to combine or to create this coupling by using normalizing flows or transport maps, in the sense that if one can create this mapping T that maps the posterior level L-1 to the posterior level L, one can create this sort of algorithms by sampling UL-1 from the posterior mu y L and then using this mapping T. Another interesting idea would be to see whether the extension of these methods to a multi-fidelity or multi-index context is immediate. One could, of course, also look at implementing other more efficient couplings, such as having, say, Hamiltonian Monte Carlo for the kernels, or using a maximal coupling of the kernels themselves and not the proposals. Or perhaps more efficiently, if one could generate maximal coupling of the posteriors of the marginals directly. Or perhaps investigating whether it makes sense to create maximal couplings in different norms that are just not the TV norm. And lastly, one thing that I would be interested in looking at would be to combine these multi-level MCMC techniques with tempering techniques, which are quite useful when you're dealing with multimodal distributions, which can lead to very nasty problems. Okay, just to finalize, some references here, mostly based on these two books here. This is the paper by Cody and AJ that got a bit ahead of us. This is Rob's very seminal paper, and yeah, some other references.